I'm very happy to have Paige North as our final speaker today. Unfortunately, she cannot be here because of some problems with her apartment. And she's going to talk about two-sided and other generalizations of weak factorization systems. So please, Paige, go ahead.
Thanks. Yeah, so thanks a lot for letting me talk in this unusual, well, not so unusual anymore format, but I really wish I could be there. Yeah, okay, so I'm going to talk about two-sided weak factorization systems and other generalizations. So again, just like Nicola and Benno's talks, I'm very motivated by homotopy type theory, but actually like generalizations of homotopy type theory. But we're kind of, as you might already tell from the title, trying to create kind of new notions of weak factorization systems. So it will be a bit more elementary than what they've been talking about. Okay, so here's the outline. So first some motivation, and then the kind of two-sided weak factorization systems that we're working on, and then an interesting categorical generalization of the whole story. Okay, so as I said, the motivation is from homotopy type theory, and as has been explained a bit in the previous two talks at least, we're interested in weak factorization systems because they, or maybe a subclass of them, the type theoretic ones, interpret identity types of Martin-Leff type theory. Okay, and so what is this project about? It's part of a larger project to develop a directed version of homotopy type theory. So we want to develop both the syntax, the directed type theory, but also semantics at the same time, and that involves developing a directed version of the theory of weak factorization systems. So that's what we're trying to do. Okay, so let's kind of revisit the story, the relationship between identity types and weak factorization systems. So first of all, like, how do we go from having a relation, or you might call it an identity type, on a category to a weak factorization system? So suppose we have like this kind of setup. So for any object X, we have a new object, gamma X. We have a morphism here. It's kind of, we can think of as pointing out the constant paths, and morphism here that we can think of as projecting to the beginning point and the end point of the path. So if we have this kind of structure that for every object X gives us a diagram like this in a category, then we can create a weak factorization system, or we can try to create a weak factorization system doing what exactly what Benno did in the last talk. We can factor through the mapping path space here for any function or any morphism f from X to Y. Okay, so I just want to point out that this introduces a kind of asymmetry, because to do this pullback here, we're using the first endpoint, and then we're projecting out of the second endpoint of this component here. So there's an asymmetry, like why didn't we use epsilon1 here and epsilon0 here? Okay, so when we talk about identity types, this is always fine because we actually have a symmetry involution on gamma X that I haven't explicitly drawn out here that preserves eta and switches epsilon0 and epsilon1. So when we think of paths in say topological spaces or in concomplexes or in homotopy types and homotopy type theory, we can always invert them, and that preserves the constant paths and switches the endpoints. So taking this factorization or the other one where we switch the roles of epsilon0 and epsilon1 is at least homotopically just the same as this one. Okay, so it's not a problem in the undirected, the normal case, but in the directed case, it is a problem because by directed, we kind of mean that we just don't have a symmetry. We don't have an involution on paths that switches their endpoints. So if we think about, and throughout this talk, I think our favorite example is going to be the weak factorization system on categories that takes which is generated by this relation, which takes a category, I guess let's call it X, and returns the arrow category. So the category of all morphisms in X. And we're morphisms between morphisms now are commuting squares. Okay, so in this particular example, we keep this example in mind where this gamma functor is raising to the arrow. This isn't resolved. So in our directed case, this isn't resolved, and we get two different factorizations. So one where we have epsilon 0 here and epsilon 1 here, and one where we've got the other way around. And now I'm kind of also writing the pull backwards because I'm thinking of a path in Y ending at a point in X. Okay, so that's what we get when we talk about, when we're thinking about directed things. We have two choices for factorization. And one criterion for this project is to see in a directed story, these two weak factorization systems as part of the same structure. So they're not, you want to not just have two free-floating weak factorization systems, but two weak factorization systems that are compatible in some way, right? And we can see they're compatible in some way. They're using the same gamma and the same epsilons, but just in different spots. Okay, now we can also go in the other direction. If we have, if we are starting with a weak factorization system on a category, we can construct a relation, the kind of the path object or the identity type in the category. So how do we do that? Well, we take, for any object X, we just take the diagonal maps. We just take the map from X, the canonical map from X to X times X. And then since we have a weak factorization system, we just factor it. We, in like classical homotopy theory, we call this the path object, but now I'm calling it a relation or an identity type. And this is important for our story because it gives us the model of the identity type, where we think of this guy as the identity type. Okay, and so in our new notion of directed weak factorization systems, we want to preserve this ability. And we can think of this as the following operation. So we can think of, let me start to write something here on the screen, if I can. So we can move away from thinking about the diagonal map here and using the product and think about like what's really going on. Well, if we think that maybe we're not in a category with products, then the diagonal map is really composed, or is really equivalent, I guess, to a span like this. And when we factor through the identity type or the path object, we're factoring this span into a shape like this. If again, we don't want to suppose that we have products. So it's kind of what's really going on in the background when we kind of unravel what it is that we're using the product to express. Okay, so I'm going to call these kinds of shapes. So this is going to be a kind of important story in this theory. So I'm going to call these spans, as they're usually called, and I'm going to call these shapes sprouts. It kind of looks like, I don't know, a little plant, and the bottom two arrows I'm going to start talking about as roots. Okay, and let me also give another criterion for what we want to accomplish here. So we can see that if we have a weak factorization system, we can, I guess I should call this delta X. We can form this diagram here, this commuting square, where this is the lambda, this is the rho, this is the lambda, and this is the rho followed by the twist map. So this actually factors, or this actually takes, if we're thinking about these guys as paths, it takes a path not to the first endpoint followed by the second endpoint, but the second endpoint followed by the first endpoint, the endpoint followed by the beginning point. So it twists these two. And the square commutes, and we have a left map on the left and a right map on the right. So we get a lift here. And if we can do this because we're in a regular weak factorization system, then this produces an involution on this m delta x, which I'm thinking of as the paths. So we can, in this case, always switch the paths. And one thing that's going to become clear as I keep going is that by considering this shape and by kind of pulling apart or unraveling this story up here and writing it as this story down here, I'm going to put an obstruction in to prevent myself from forming this kind of lift and being able to invert the paths. Okay. Let's see. All right. So that was a bit of like the motivation and kind of a review of how things work in the normal weak factorization system case. So now I'm going to talk about two-sided weak factorization systems. And here I'm going to compare this theory to the usual theory of weak factorization systems by putting the kind of classical weak factorization system stuff in gray boxes and the new stuff in blue boxes so that like we can compare it easily. Okay, so normally in a weak factorization system, we have a factorization of every morphism into a composable pair like this. And I'm going to say that this is functorial, so it extends to morphisms and morphisms. And in this new theory, like we started in the last slide, with this one operation that we wanted to preserve, which had this shape. And we had identity arrows in that slide, but now we're saying that for any sprout, for any two arrows we could put here, we have for any span, for any two arrows we could put here, we can factor this span into a sprout. So we get a diagram of this shape such that this composite is F and this composite is G. And again, we want this to be functorial. Okay, so just to reiterate, we can now factor a span like this, kind of diagonal, into a sprout like this. And conversely, if we have a, oh, I think I should maybe go forward really quickly. Let me just talk a bit about notation because it's showing up in the previous slide. So just for a bit of notation, I'm going to write a span like this as inline, because that will make these diagrams writable, as f comma g from x to y comma z. And then a factorization we can write inline like this. And this is just notation, but secretly we're in this common category. Okay, so I'm using that notation here. So if we start with a reflexive relation like this, and now I'm not, not supposing that I have products, I'm just supposing I have this pair XX, then given a sprout, I can form, given a span, I can form a factorization like this by doing something very similar to taking the mapping path space. So the mapping path space usually just looks like, usually it just looks like this guy. But since I have kind of this two-sided thing going on, I'm taking a path in Y that ends at a point in X, and then a path in Z that begins at that same point. And this we can think of as the collection of all those kinds of paths, with the projection here to the beginning point of these paths and the projection here to the end points of these paths. Okay, I just went over this slide. All right, so now we can talk about what we mean by a lift in this strange version of weak factorization systems. So normally in a weak factorization system, we talk about commuting squares, then we talk about lifts here. And in this theory, now we're going to talk about specific shapes on both sides of the square. So on this side, I am always going to be considering a sprout. And on this side, I'm always going to be considering a span. And then I'm going to say that a sprout lifts against a span like this if there's, if for any two arrows here that make the whole thing commute, this, there's a lift like this that makes both, well, this triangle and this square commute. And it should be clear here that this map here, or this arrow here, is standing for two maps, one from C to Y and one from D to Z. So it's a map in that category, C times C. Okay. And now we can define fibrations. So I guess there are different ways to define it, but I'm going to define fibration in a classical way like this. So F is a fibration if when we factor it and put those factors here and identity here, we get a lift. And then I'm going to say that a span, FG, is a two-sided fibration if when I put its factorization here, which is a sprout, and identities here and here, so it's a little bit different because there's identity here, then I get a lift here. But we can kind of imagine this diagram here is kind of being shifted around so that the row FG is on the bottom from MFG to YZ, and then it looks basically the same as this one. Okay, and now we can see that we're not going to be able to form this this lifting problem that allowed us to involute the paths, right? Because if we take x, say M11 to XX, and then I want to put here, what do I want to put here? M11 to XX is going to be the lambda, the left-hand map of factoring that identity span. So this lifting problem is analog to the one where I derived an involution on the paths, an inversion of the paths. Right, but now I cannot, like the place where I want to put the twist is here, but I cannot do that, right? Because it could put, let's see, I could put any arrow before I was just drawing it as one arrow, but it really stands for an arrow from the first X to the second X, and an arrow from the first X in the first part to the to the first X in the second part, and from the second X to the second X. And that, since I'm kind of rooting, I'm going to use this word later, rooting this story in this kind of configuration of the X's, and since maps are only allowed to go from the first one to the first one, the second one to the second one, I just can't twist them anymore. I can't send the first one to the second one and the second one to the first one. So I put in an obstruction that doesn't allow me to derive an involution on the path space. Okay, so now I can talk about cofibrations. So classically, a cofibration is a map C, such that if I factor it and I put the identity here, then I get a lift. And maybe I should say, just to be clear, I'm using the word cofibration when usually people use the term left map, and fibration when usually people use the term right map for just a weak factorization system. So there's no model structure here or anything. But since there's no model structure, I'm just going to use cofibration for left map and fibration for right map, because it gets it's a little bit easier to say. Okay, so that's what's going on classically. And then a rooted cofibration is a sprout. So I'm kind of thinking of B as being the cofibration and rooted by maps into CD that restrict the maps, like the ways that I can kind of go forward onto this side, like I just talked about in the obstruction to twisting. Okay, so I'm thinking about B being rooted by these maps CD. And if I factor this, actually, we have to factor a span, and here we have a sprout. So we compose this sprout to get a span. So we look at the sprout CB and DB. So just the sprout from A to C and A to D, just like forgetting about B. We factor it, and we put it here and the identity here. If there is a lift here, then we call this guy a cofibration, a rooted cofibration. Okay, so it looks almost the same as this picture, except we have to do some composition before we can factor, and we call that a cofibration. Okay, then there are some results. Maybe I'll just go through this quickly. So when we have a weak factorization system, we have some basic left maps and right maps, which are isomorphisms. They're always closed under retracts and composition. The fibrations are stable under pullback. Co-fibrations are stable under push forward. And the co-fibrations, of course, lift against the fibrations. That's kind of the main point. And so in this theory, we have all the same kind of results. So a sprout, so playing the role of this first thing is the fact that a sprout whose top morphism is an isomorphism is a rooted cofibration. So the bottom maps, the roots can be anything. The analog to this for fibrations is the product projection span from X times Y to X and Y. That's kind of the primordial two-sided fibration. We can take the span composition of two-sided fibrations. That's still a two-sided fibration. Two-sided fibrations are stable under pullback, and the rooted cofibrations lift against two-sided fibrations. Okay, so just defined the notion of factorization and cofibrations and fibrations. And now I want to talk about a weak factorization system. So we need some extra properties. So we could define a weak factorization system classically, not always defined this way, to be a factorization like this, such that each guy in the image of lambda is a cofibration, and rho f is always a fibration. Maybe I should say, when I say it's not always defined this way, I mean that this isn't the exact definition that's written down, but this is equivalent to the definition that's any definition that's written down that I've seen for a weak factorization system. Okay, so we want to emulate this formulation of the definition. And we say that a two-sided factorization, lambda rho, is a two-sided weak factorization system if the span like this that we always get from a span FG is a two-sided fibration. I'm just saying that anything in the image of rho is a two-sided fibration. Okay, and for maybe technical reasons, I'm just going to separate out the notion of cofibration, or like the similar restriction on cofibrations. So we say that a strong two-sided weak factorization system is one not where each lambda f is a cofibration, because strangely the lambda f is just, let me draw this. The lambda f is just in our two-sided fibration case. So maybe I shouldn't be drawing it in the gray box. Let me draw it over here. So lambda f is just a morphism. So if we're asking whether it's a cofibration or not, we might be asking whether it's a cofibration rooted by the right-hand side of the factorization rho f. And strangely, it's always a cofibration. So that's why I'm not making that additional requirement here. But in order to make some nice things work out, we can ask that it's a rooted cofibration rooted by these other maps here. Okay, and let's think about this a little bit. So I talked about in the beginning how we have, say, in the category of categories, with the path object given by taking a category to its arrow category. So kind of the path, the interval is just the free arrow category. So that's our favorite example. And we saw that there are two weak factorization systems in that category. One that's given by this particular mapping path object where we use the epsilon0, and the other one where we use the epsilon1. And we want to have a theory where those two things come together and are part of one structure. So now if we have a two-sided weak factorization system, we want to derive that kind of structure out of it. So we want to, from a two-sided weak factorization system, project out to get two different weak factorization systems. And we think about the two-sided weak factorization system as being like the story where they're both there, they're both interacting, and then we can kind of project out to either one. Okay, so how would we do that? If we look at this factorization of an arbitrary span FG from X to Y and X to Z, we could kind of try to erase or forget about Z here and just take it to the terminal object. And then we get a map to the factorization of this span that we're looking at the factorization of this span. And of course, the right-hand side of the span is trivial. So it's really only something about this map from X to Y. And similarly, we can kind of project out to a factorization of this span, which is really just a map from X to Z. So we always kind of have this projection to these two factorizations of just maps. And for technical reasons that are kind of hard to explain, this will all behave nicely if we ask that this lambda is a cofibration rooted by these two guys. And we have enough leeway to prove things that we want. Okay. So again, we have a nice theorem by Rosicki and Tolan where they show that in a weak factorization system, if we define it in the way that I defined it, which is a little bit unusual, then we can prove that the cofibrations are exactly the morphisms with the left lifting property against the fibrations and vice versa. Usually the definition of weak factorization system looks more like this, and you can derive the way that I defined it. But anyway, in this theory, we can also get the same kind of theorem that in a two-sided weak factorization system, the rooted cofibrations are exactly the morphisms with the left lifting property against the two-sided or the rooted, I should say, cofibrations and vice versa. And like I just suggested 2 slides ago, we can always project out to the two different weak factorization systems. And now I should say that I have a typo here. I want to qualify this with the word strong. So the strength is giving us this property that something is a cofibration, which allows this whole story to behave well. Okay, so if we, just like we had in 2 slides ago, if we kind of think about a map XY as constituting a span like this, then we can use our factorization of spans to derive a factorization just of maps. And so similarly, we can do it in the other way. And these correspond to the 2 different factorizations that we talked about at the very beginning of the talk. And so we can call these, following some people who've worked on directed homotopy theory, future weak factorization systems or past weak factorization systems, because we can lift along paths that are either going forward in the future weak factorization system or going backwards in the past weak factorization system. Okay, so we have some nice behavior for a strong. Again, I want to qualify all these two-sided weak factorization systems in this slide with strong. So if we have a two-sided vibration and a strong two-sided weak factorization system, then F is a past vibration. So the left-hand leg is a past vibration and the right-hand leg is a future vibration. And we can kind of put them together in a sense. If we start out with a two-sided weak factorization system, a two-sided vibration in a strong two-sided weak factorization system, then we can compose along past vibrations and future vibrations. And we still end up with a two-sided vibration. So vibrations in this strong two-sided weak factorization system are closed under composition in that sense. Okay, so we can think about, as I've been suggesting this whole time, our favorite two-sided weak factorization system in the category of categories. So say we have a span of categories like this, C, D, and E, then we can think about the relation that's given to us by taking a category C to the arrow category of C. And this produces a factorization of spans where we take, where this middle object has objects, an arrow in D that ends at, well, let me write this out here. So we have an arrow in D, maybe I won't give it a name, so let's call it D0 to D1, an object in C, and an arrow from, let's say, E2 to E3. So this is in, this arrow is living in D, this arrow is living in E, this object is living in C, and F of C is equal to D1. So this arrow in D is kind of ending at the image of C, and F of C is also equal to E2. So this image, this arrow in E is starting at the image of our object C. Okay, so it looks like these 2 paths, one in D and one in E, that don't really begin and end at the same place because they live in different categories, but they, in some sense, begin and end at the same place in C. Okay, so if we look at this, the past vibrations contain the growth and decay vibrations, or the retract closure of the growth and decay vibrations. Benno talked about this a little bit in his last talk when he was talking about in an algebraic weak factorization system, that's almost the same as this one, but here I'm just talking about a weak factorization system. He's talking about the split growth and decay fibrations as being the fibrations. And the future ones correspond to the op fibrations. And then the two-sided fibrations are almost exactly the growth and decay two-sided fibrations that Street introduced in his paper from 1974 that some people might have heard of. So the relationship between these two-sided fibrations that we're talking about and the two-sided fibrations of Street, to which I'm going to add the adjective growth and decay, relate in exactly the same way as the past fibrations relate to the growth and decay fibrations. That is to say, in this standard weak factorization system, the right class, which I'm here calling the past fibrations, are the retract closure of the growth and decay fibrations. And here our two-sided fibrations are the retract closure of the two-sided fibrations of Street. Okay, and then this is maybe a bit more, getting more detailed, but I wanted to kind of connect it up back to like the kind of, I don't know, dialectic between weak factorization systems and mapping and relation slash mapping or slash path objects slash identity types. So this is a theorem that I proved in my thesis that was about this correspondence. So if we have a weak factorization system, then we can show that it's generated by a functorial reflexive relation like this that we talked about in the beginning of this talk. And you need some hypotheses on how this relation behaves to actually get it to do that. And this is equivalent to a condition on the weak factorization system that it be type theoretic, which just means that all objects are fibrant, and a Frobenius condition that the cofibrations are stable under pullback along the fibrations holds. Okay, so we have a similar result for strong two-sided weak factorization systems. We need a kind of unfortunate hypothesis that the factorization of the trivial span is trivial. Hopefully we can improve that. But that, for example, holds in our favorite example. We can, if we have a functorial reflexive relation, that's just the same data as up there. But now that is weakly left transitive, weakly right transitive. So we can see that here we had this hypothesis symmetric, which made like the left, and I'm not explaining what this means, but I'm just telling you that the hypothesis of being symmetric made like left and right be equivalent. And so here we drop the hypothesis of being symmetric because we're directed. And then we need to hypothesize that we're both left and right, these things, transitive and connected. And then this is equivalent to what I'm going to say is the two-sided weak factorization system being type theoretic, which is that all objects are fibrant. So all objects being fibrant just means that this span is a two-sided fibration, and that the two-sided Frobenius condition holds. And this one is probably less obvious. So let me explain what that means quickly, because maybe it's kind of interesting. So the one-sided, the regular old Frobenius condition said that whenever we pull back a cofibration along a fibration, it's still a cofibration. Now the two-sided Frobenius condition says that if we have two cofibrations like this that are composable in the just in the sense that they share this object here, and this guy is a future fibration and this guy is a past fibration, then we can kind of in a sense take a pullback of this, both of these cofibrations, I guess, along a fibration kind of in some sense, and take basically you might say a composition of these two things to get a sprout like this. And the Frobenius condition holds if whenever we do this, we get a cofibration. We're just taking the pullback here of this cospan to get this guy, and then of this cospan to get this guy. So in some sense, we're kind of composing these two spans together, or these two sprouts together. Okay. All right, so that was it about two-sided weak factorization systems. Just looking at the time. Okay, so some time left. And the question is now, how do we algebraicize this? I'm not sure how to pronounce this word. Algebraize this. Some people in this workshop have been talking about algebraic weak factorization systems. And in this talk so far, I've just been talking about a generalization of the notion of weak factorization system. So of course, the question is, how do we make this more algebraic? How do we get to something like an algebraic weak factorization system? Okay, and so, oops. There we go. Okay, so that brings us to the generalization of this story, the kind of categorical account of what I've described in a very hands-on way. And this is joint work with Benno Vandenberg and Aaron McCloskey. So, okay, let's think about what we just did. We can think about the functor that takes a span to its right factor. So let me draw this out. So if we have a span like this, we can take it to its right factor, which we're calling rho FG, and here also rho FG, maybe rho 1 and rho 2 FG. Okay, so this functor underlies a monad, and I'm giving reference here to Street because he did this in our favorite example of cat. And so he talked about the algebras for this monad, and he defined those guys to be two-sided fibrations in his sense, which I give the name now Grothendieck two-sided fibrations because they correspond to Grothendieck fibrations and Grothendieck op fibrations. Okay, so that works perfectly. Like that corresponds perfectly to what we expect for an algebraic weak factorization system. Okay, but the left-hand part is really messy, unfortunately. In particular, the shapes that we have going on aren't taking things of one shape to things of the same shape, right? So it's not an endofunctor. So that's like the first, a big obstruction to it being a monad, right? So what is the left part actually doing? Should it produce, like so, if we look at, again, a sprout like this, or a span like this, then we have here the left part, and here the right part. Stop writing F and G. Let's say row 0 and row 1. So we have the left part and the right part. So here we start with a span. And I guess there are different options. We could say that it takes the span to this map. But those two things, the span and the map, are different shapes. They live in different categories. Or it could take the span to this whole thing. Those still live in different categories. And of course, if we say that we want to take the span to this guy, I mean, we're already talking about that. We've already covered that in this thing. That's the monad part. That's the right part, not the left-hand part. Okay, so since these things, since the factorization takes things in one category to things in another category, it's not an endofunctor. It doesn't make sense to talk about it being a monad. But what does make sense to talk about is, I think, not so well known, but has been developed relatively extensively, is the notion of relative monad, which reduces in the case when we're looking at endofunctors to those monads, but also allows us to talk about monad-like things that have for functors that have different domains and codomains. Okay, so that's what we're going to use to at least fix up the left part. Okay, so let's explore what I mean and what Benno, Aaron, and I developed by some examples. So, okay, we can think about, again, we're in the category of, or yeah, so let's just say we're in the category of categories here. This is now not part of the weak factorization system, but we're taking a category to its arrow category. And here we're taking a category to the category of diagrams of the shape. That's there noted in the exponent. Okay, so we're not thinking about this as being part of the weak factorization system, but defining in a categorical way what a weak factorization system is. Okay, so we have this functor that goes from right to left that takes two composable arrows in a category C to their composition. That's why I'm calling it circle. And a factorization, first of all, so I'm not talking about weak factorization systems yet, just a factorization is, of course, a section that I'm going to call F of the composition map. And then we could put accents on that, and that becomes a weak factorization system, and maybe even an algebraic weak factorization system. Okay, but we also have these two other functors that are going to play a role in our story of relative monads, which is in right and in left, I guess I'm calling them. And so in right takes a functor from x to y and produces, let me write this slightly differently. So if we apply this, I guess, to x and y, so f from x to y, then we're going to just, there we go, okay. We're just going to produce a pair of composable arrows from F by putting the identity first and then F. And similarly, in left puts F first and then the identity. Okay. And these happen to be, I mean, they're so simple and nice that, of course, they constitute left and right adjoints to composition. Okay, so what is this doing in our theory? So first, let's talk a little bit about what an algebraic weak factorization system is. So first of all, so let me draw in some extra stuff here. There we go. Okay, so if we have a section here, F of circle, and of course, in left and in right, they also constitute sections of composition of circle. And so by which I mean that, first of all, the unit of this guy and the counit of this guy are identities. So an algebraic weak factorization system asks that F underlies comonads, in the sense that if we do F, and then I think here we have projection that projects out the second arrow, and here, and this is left adjoint, I'm pretty sure, and this, we have a further right adjoint that projects out the first arrow. So when we talk about algebraic weak factorization systems, we're asking that, let's see, we're asking that this composition here underlie a monad, and that this composition here underlies a comonad. Okay. And then in our new relative story, we're going to ask that instead of asking that this composition underlies a monad and a comonad, we're going to ask that F itself underlies a monad relative to in R, it's this left adjoint, and a comonad relative to in left, this right adjoint. Okay, and so what does that mean exactly? I'm not going to define the notion of relative monad and relative comonad, but I'm just going to tell you what it is in this case. So F underlies a relative monad if given a morphism of this form, which I'm illustrating here. So a morphism of this form in right is this guy. The factorization I'm writing as lambda and rho as usual on this side, and a morphism consists of three maps like this that make everything commute. So if given a map like this, we can produce a morphism of this form, FF to FG. So we factor F and G, satisfying some axioms that I'm not going to write down. And so we can note that something that's maybe I've written a bit subtly here, which is that these A's have to be the same, kind of the boundaries have to be the same, the A's and the C's have to be the same. And so we're tasked with, we're trying to figure out if this is a relative monad, we're tasked with producing some morphism here from B, I guess, and all the other data. So the B and the B prime don't have to be the same. And we know that, say, if we're in a weak factorization system, we know, of course, if we're used to doing, or we know that we can do this if we're used to doing kind of algebra with these kinds of things. We can factor F into LF, maybe draw that, and factor F into lambda F and rho F. And then we can think of the bottom square, and kind of shift it in our minds as being a square between lambda F and rho G. And then we find a lift like this. And that's exactly the B prime that we're looking for. Okay. So this corresponds to things that we can do when we're in a regular old algebraic weak factorization system. Okay, so when we're in this new kind of weak factorization system that's defined by this kind of relative monad comonad thing, what does it mean to be a fibration or a right map? So now we are going to talk about, if we just kind of look at the notion of relative monad and the notion of algebras for relative monad that's already been defined by other people, and we just apply it to the situation, we get the following, which is that a fibration is a composable pair, FG, such that for any morphism of the form in right Z to FG, which I have drawn here, there is a morphism from FC to FG, also satisfying some axioms like this. And you might note this, it looks very similar to the diagrams that we had before. Now we have just an arbitrary, or maybe I want to say, we are asking that a pair FG behaves like a factorization lambda rho, like we had in the previous slide, in order to be called a fibration. Okay, and then we have the dual definition for cofibrations, and we can show in this theory that fibrations lift against cofibrations. Okay, so it's looking pretty strange so far. But we have a nice theorem that compares these things to usual notions of algebraic weak factorization systems. So an algebraic weak factorization system produces a relative weak factorization system. We can always produce a relative one from a usual one. And given such a relative weak factorization system, so given one that is produced from an algebraic weak factorization system, if we look at composable maps of this form, so we have an identity and then an arbitrary map, and we are wondering which of these guys are fibrations, it turns out, as we would hope, well, almost as we would hope, I guess, that the composable pairs of this kind of form are fibrations if and only if F is a fibration in a weak sense, if and only if F is an algebra of the pointed endofunctor underlying the monad part of the algebraic weak factorization system. Okay, this is quite nice in some sense, because in some sense, the composable pairs, which are fibrations of the form 1F, correspond to right maps in our original weak factorization system. But it's also a little bit unsatisfying, because I'm talking here about algebras for the pointed endofunctor, not algebras for the monad. And so, I don't know, this is very interesting to me, very kind of unsatisfying, but also strange and interesting, because we're doing something very algebraic. We have functors, we have not exactly monads, but relative monads, relative comonads. And when we look at the algebras, where we're covering the notion of right maps and left maps of a plain weak factorization system, not algebras of the monads and coalgebras of the comonads that constitute the algebraic weak factorization system. So it's matching up with the classical unalgebraic version, even though this new thing is quite algebraic. Okay, right, so I'm almost at the end, right in time, I think. So in general, if we have a pair of adjunctions like this, such that kind of emulates our situation before. So this J is playing the role of composition, I is playing the role of in right, and this is in left. Now C and D can just be, you know, any categories, don't have to have any special relationship to each other except for these functors between them. Such that this is supposed to be a turnstile. I don't know what happened to the top of it. So I is going to be left adjoint to J, and we're asking that J is left adjoint to K. And we're also asking that I and K are sections of J. So by which I mean that the unit of this and the co-unit of this are identities. In this situation, we define a relative weak factorization system, or we say that this is a relative weak factorization system if we have a section of J from C to D that underlies a monad relative to I and a comonad relative to K. We're just abstracting the previous story. And we can show some nice properties of this, maybe the nicest of which is what we would hope, which is that once we define all the things that we did before, like vibrations and cofibrations, we can show that cofibrations lift against vibrations. Okay, and now back to two-sided weak factorization systems. So why, maybe now this explains why we were kind of led to this general setting by trying to understand two-sided weak factorization systems algebraically. We have an instance of this setup. We have here, so this logical and symbol is supposed to be representing the diagram of spans. So here we have the category of spans in some category C, and this symbol is supposed to be representing the diagram of sprouts. So here we have the category of sprouts in some category C. We can always compose a sprout to get a span. We talked about that a little bit before. We can kind of do an in-right thing where we take see if I can write something here, where we take an F and a G to an F and a G like this, where the top map is the identity. And on the bottom, the right adjoint is a little bit different. So we take a span like F and G, let's say now, I should probably give it names, to X, Y times Z, and then the projections to Y and Z. So that's the right adjoint of composition. Okay, so if we just apply the definition that we had before of relative weak factorization systems, that corresponds to a two-sided weak factorization system in the sense that I defined in the middle part of this talk. And we also have nice correspondence theorems. So the fibrations of the form 1FG, so that's, I mean, something of this form, correspond to the two-sided vibrations that I talked about before we started talking about this general setting. And the cofibrations correspond exactly to rooted cofibrations. Okay, so that's it for my talk. Thanks a lot. Any questions?
Questions? Yeah.
Yeah, so my first question is a little bit about just the connection with directed type.
Can you hear the question or?
Not very well.
Okay, maybe I should repeat it after the question.
Thanks for the talk. Yeah, so I have two questions. The first is about your connection with directed homotopy type theory. So you have defined let's say in normal homotopy type theory of the comprehension categories, in which in particular you have a vibration. And since in your version of directed type theory you also have your opposite context, is then let's say a suitable notion of a comprehension category for directed type theories, and all contain, instead of a vibration, this notion of two-sided vibration, or?
Yeah, good question. So this is kind of difficult because it kind of explodes. So yeah, so normally if we, I don't know, we have some dependent type like this in type theory, right? So as you said, this is represented semantically by a fibration. So now in directed type theory, which is, I've put some papers out there about this, but it's not quite worked out completely. So we could have B dependent on X in say a covariant way or a contravariant way. So we might like kind of notate in some sense how B is depending on A, and then in this case it might be represented by a Grothendieck fibration. If it's covariant, we might represent it by a Grothendieck op fibration. But then of course, like if we consider a kind of directed identity type, which I'm often calling HOM, then just like in category theory, the X is contravariant and the Y here is covariant. So this is depending on, say, two variables here, where this guy is covariant. I guess I wrote op before. Let me write op again. This guy is covariant. The X is playing a covariant role, and the Y is playing the X is playing a contravariant role, and the Y is playing a covariant role. And so this would be well represented by a two-sided fibration. So that's why we're talking a lot about two-sided fibrations. But then, of course, you could imagine some type that depends on a whole bunch of variables, some of which are covariant, some of which are contravariant, which depend on each other in interesting ways. So you might, first of all, imagine like not just spans. So this, like we could think of this as like HOM XY, kind of the big sigma type. This is like a two-sided fibration. So we could think of like not just spans, but things that look like spans, but have like many legs, right? Some of which are like off fibrations, some of which are fibrations. So not two-sided fibrations, but n-sided fibrations, or things which have, you know, even more dependency going, you know, where these types are dependent on other things. So maybe this project is like the first step into understanding, and one reason why I'm interested in the generalization is like, we want to understand crazy diagrams, not just spans, and what it means for those to be fibrations. Yeah, so good question. Is leading into a lot of stuff that I'm interested in.
Also, thank you for the answer. It seems indeed very weird phenomenon to make it precise.
Yeah.
Hi, Paige. In the last slide, you said correspond. Do you mean are exactly?
Yeah, so I think so this instance of correspond it's not clear what that means because they're completely different kinds of structures. But in these two instances, I mean exactly. Yeah, so these classes are the same. And so again, we're seeing the phenomenon where I mean, there's no notion of real algebraic two-sided weak factorization systems, but this notion I gave looked very unalgebraic in the middle part of my talk. And so these fibrations, these algebras for the relative monad are corresponding again to those like really unalgebraic fibrations.
And a little earlier, you had instead the classes of Grothendieck fibrations, say, being contained in some of your classes. Do you know what else is in there?
So you mean these points or this point? Well, I guess all the 3 points are really the same, yeah. I think. So the past fibrations, the right class of this kind of canonical weak factorization system on CAT is the retract closure of the Grothendieck fibrations.
Okay.
So yeah, what else is in there? I don't know, but that helps me understand the relationship.
Yeah, thanks. Good to see you.
Yep, good to see you too.
No? Okay, then let's thank Paige again.